All right. So thank you for joining. Which papers am I competing with today? In terms of the securities talk, probably. Anyway, this is formally the last lecture in this course. That said, you probably get some heads up in terms of exam and other things. Plus, there is obviously the presentations that right course, wrong course, hang on. Yes, there was presentations here as well, right? That you need to provide. But in terms of input, in terms of moderately exam relevant stuff, that must be the last session. We're kind of obliged to commit to that. So, and quite fitting, I will talk about something we haven't even we haven't really spent time on at all, which is graphics programming. And I say it's quite fitting because we just now had a quite interesting talk about Vulkan in the context of graphics programming. So shedding a different light on what's coming next. And as a word of warning, that's coming to mobile devices as well. That said, I will not spend time talking about this in the first place. And in fact, we'll only look at graphics from a very high level perspective on mobile devices, because I think none of your projects actually actively uses it, and it comes with a lot of challenges. But I just want to highlight those with respect to the use on embedded systems, tablets, mobile devices, and the like. Cool. Anything else I wanted to say? No. Good. For now, we're good. Right. So the use of graphics in mobile devices is actually not a novel concept, right? So do you guys remember your first graphic application or app, as we call it nowadays, on mobile devices? I'm just checking about your, when you were roughly able to follow the trends at the time. What was the first popular mobile phone game you know?
Doodle Drop.
I heard something. Wait, there was some
Snake.
Snake, right? Yes. Okay. So did you play it yourself? Yeah. You guys as well, right? So there's this generation that played Snake, and then there's the generation that just implemented Snake, right? So because the lecturers forced them to, but they actually don't know the game itself, right? So, but cool, right? So Snake was one of them, and graphics has come a far way since then, right? So Snake from the implementation, how it works, the principles are quite straightforward, and it's going beyond the idea of just having some sort of simple user interaction, but you actually need to draw something, you need to render something that is not text, meaning some sort of shape or pixel in a wider sense on the mobile device. And it's usually much more complex, because instead of having fixed items that support your layout, for example, in a textual manner, where you don't need to do much more than rather providing the text and the rendering is done for you, it's actually in part your role to do that as well, right? So you can have much more complex representations, including text, graphics and background, and things like this. There are some helper mechanisms, such as, for example, animations for reasonably static menus to make them appear more dynamic and have some transition functionality. But overall, it's still kind of straightforward and not really too exciting. More interestingly, obviously, is when we're looking into games. And only few of you, I think, develop actually games. So there are some groups I know that do some games, but that's where the graphics obviously comes more into play. But even there, given the performance of mobile devices nowadays, in many cases, depending what you intend to do, the performance is sufficient if you're not looking for highly sophisticated games to just do it in 2D in the first place, like in the ball example, for example. So, and the idea is here that I'm briefly looking into the basic history of images. So that's something that's motivated as part of this lecture, and then shift incrementally towards 3D representations in mobile phone, right? So again, 2D would largely look at animations, whereas three-dimensional aspects would think about space, right? So you have a spatial representation of objects that you need to project on a 2D screen, right? Before I continue, just a question: how many are doing games or applicazione here? So games people is that crowd. You guys application mostly? Cool. Okay. So did you have graphics before? Oh, okay. Okay. So that's helpful. So in a 3D situation, right, we're actually modeling object in space. So we're thinking about the three-dimensional space logically. but then we're reducing it to a two-dimensional space to, for example, model the fact that something is obscured by something else, or that we occasionally only see a part. We have a field of view that we can eliminate the rendering or even consider computation of objects that sit outside my field of view. So a lot of those transformations related to this orientation needs to happen as well. So apart from the simple rendering, which in 2D is relatively straightforward because the field of view is clearly defined and usually there's no depth concept. Well, there is some layer concept often, but not really depth concept. So it's quite a bit more complex there. So, but we go into that a bit later. But images have come a long way, right? So the idea of visualizing something is, as you're probably pretty aware of, is it started with caveman paintings, and I think amongst the best documented on the center of France. I forgot the name right now. Does anyone have it on the tips of the tongue? Anyway, it's in France, and the idea is there that it started off quite simple, basically by having fixed iconic meaning or fixed meaning associated with particular representations, right? So it was very clear how in a drawing, for example, a horse had to look like, right? So there was not much artistic refinement or individual interpretation. There was kind of a fixed convention on how something needs to look like if it's supposedly being a horse, most likely having a head, 4 legs, and some tail-like, element. And we're actually coming to that back if we think about structures in Android, for example, buttons and the like. They also work on the iconic basis. It's not so important to be necessarily artistically refined, but that the meaning is unambiguous, right? So meaning first and aesthetic second. And they are often not only in the use of their elements, but also in their orientation, were actually quite straightforward. If you, for example, look at all those images, do you see any convention that you would be able to identify? Note that those images are across a spread then of more than, probably 5,000 years. But they still have some sort of conventions. Do you see any of those?
Black and white background. Rectangular.
Rectangular. Okay. Yeah. What's another one which I find very interesting?
They're all battles.
There's hunting scenes. I'm not sure if that is.
They have a frame.
Sorry?
They have a frame.
Well, the cave painting doesn't have a frame, so that's just an extract, a picture basically taken. But if you look at directionality, direction.
They're all kind of orthographic.
Yeah, good. Okay, with no 3D, I got that bit. Yes, cool. So it's a 2D painting, yeah, but like 2D, intentional.
There's not a lot of perspective in there.
Yeah,
it's all just one layer.
Cool, right.
That's what I meant by.
Okay. You're right. There's no. You're right. There's no orthographic projection. There is actually no dimension in there. Instead, they work with convention. But the other thing that I wanted to highlight by convention is they all kind of operate from the left to right, right? So all the pictures, so which is quite interesting. But what Jonas pointed out there is actually quite right. So the idea of having a 3D space in which objects move around was actually not given, right? So, and that's quite obvious if you look at. So where is it very obvious that they struggled with 3D space in that image? Do you see? Question is, what can you see in the first place? Yeah, Ella?
The trees.
Yeah. Okay.
Like the same size.
Yeah, that's right. So no variation over size. Yeah. What else? Anything else? Very noticeable on the lower right. And you know that pattern, and you'll find it commonly in those kind of early medieval paintings, I guess. Well, the crossbows are drawn sideways, right? So because they couldn't accommodate the 3D representation of the crossbow, so they drew it sideways here. And this is quite common for a lot of paintings of that time, right? So they knew the problem, yeah. So, but they worked around it by having conventions, so people know if you draw this thing, it means it's a regular crossbow, right? So, independent of its directionality and what particular items mean and so on. So it was quite relevant. And then, as Jonas suggested, at some stage someone came up with the idea, hey, we can you know, see 3D, so why shouldn't our pictures do that as well, right? So the idea, how do we represent perspective? And hang on, when was that? 14. Yeah, Bruno Skelly, he was the first one to be known for it, but there was Alberti, which was a painter, which was giving explicit instructions of how to actually come up with the idea, and that was the concept of having a very simple linear projection idea, and that means that there was some focal point, or needed to be some focal point in the picture towards which parallel lines were drawn. So we see that in this Da Vinci painting, lightly indicated. Ah, yeah. Yet another students. I'm fighting for all of them. If you find more, please go for it. So, so we see that we have a focal point, and all the lines are basically linearly oriented towards that, and that gave the painter the an intuition, at least, as to how size needs to be represented. Right? Objects further away, closer to that vanishing point, obviously smaller, and the ones closer, a bit larger. So it's a bit more of a mathematical concept introduced into painting, and has simply been absorbed into the best practice in that particular context. So yes, perspective. So we're getting closer to 3D, don't we? No? Okay.
Yeah, it always fascinated me, like how long it took humanity to do that. Like we take it for granted that there is perspective. Like kids know it in the kindergarten, but you know, until like 15th century, people didn't work it out. They painted stuff like really stupidly, right? And it's like something so basic that we take for granted that took humanity, like, you know, thousands of years.
Exactly. Yeah, we're just coming from that one.
Yeah,
so,
exactly.
Yeah, so yeah, so we made quite a bit of progress. But it's a reasonable motivation for graphics context. Yes. So we need to think in perspective, right? So that's the important thing we need to get out of this. And okay, how do we do the actual? So now I'm a bit daring here. I will call that, how do we do computer vision? So in the widest sense, that's probably one of the first examples. The idea being there, how do we record reality, right? So you guys all know from probably physics, the camera obscura concept. You built one yourself, perhaps? No?
Oh.
You guys did? You guys? No? Okay, idea as follows. You have a closed box, right, with one opening which admits light as small as possible to focus rays, and then it's exposed to you know, light and an object, and the idea that's completely dark inside, but you need to have some sort of projection surface, and the idea is there that you will have an inverted version of the object you are actually, you know, trying to observe inside that very camera, and then you can use some way of, you know, drawing drawing around this particular shape. So we actually did a realistic drawing of a existing object, obviously to scale, right? So, but you know, this is I think a reasonable starting point for thinking about photorealistic, well, paintings, if you like. And well, the idea is yeah, it's literally shown here on the top right, right? It's quite straightforward. So you have light passing through a point, and based on the different depths of the camera obscura with respect to the physical perspective, you have a scaled down version, or referred to as perspective projection of the original, right? So it's basically the idea that the difference in depth is determining the size of the corresponding object in the end, right? Cool. Is there anything else? Which makes it quite obvious from an observer point of view, if you motivate this, that obviously anything that sits in front of something else, if it's scaled over distance, it obviously occurs in different sizes. So that's the idea. In 3D, we're talking about the did we talk? Yeah, we did, right, guys? Yes. Sure. Okay. Cool. Default. Sure. Possibly. In lecture 2, we did. Yes. We talked about perspective projection, and the idea is precisely that, right? So we're looking at, if we project, for example, we have a object in a distance, and we want to project it on a closed 2D plane. We determine the point x, for example. Hang on. The point x, but simply by dividing the distance from the plane by the actual z value, meaning the distance to the object from the observer's point of view. And this way we get a perspective projection of the x value and the corresponding y value onto the two-dimensional plane at a fixed distance d, for example, right? So quite straightforward. It should be intuitively accessible, right? So I take that as a yes, or I don't know. I think I fell asleep. I go home, see if I'll come back in 30 minutes, see if they notice. So, all right. So, okay, so we have projection ideas. We have the idea that depth is important, right? We need to represent it somehow. And we have the idea of representational conventions. So, but how does the computer actually see? It's an open question. I don't know either. So come on, I'm waiting. So, so there was some.
It records light values in pixels.
Yep.
A lot of small sensors that records the light values.
Cool. Yep. Any extension from down here? You want to say something?
No. More or less same thing.
Same thing. Okay, whatever, right? Same thing. All right, cool. So how does the computer actually see? Yeah, and you're actually kind of spot on, right? So whereas the human has kind of a very subjective and gestalt psychologically inspired perspective, right? We know that there's possibly a locomotive on the left side. The computer doesn't care, right? So no semantics attached, no model, no shapes as such. It's just about the lighting information, right? So or we referred more like nowadays. In a color image, obviously, color information is associated, right, with this. So brightness plus color, basically, as the mechanism. So the computer basically reduces this on a pixel basis. So we have some sort of fixed metric, fixed frame that we apply to a image, and then determine the individual values and the size of those pixels, as let's call them now. Determine the resolution, right? So, and how detailed our representation fundamentally is. And if we look at the fact that the human eye actually perceives 3 colors as opposed to just contrast, so because we have the rods and the cones, whereas the rods are largely responsible to sensing brightness or lighting, as you mentioned before, brightness basically. The cones are responsible for differentiating this information into colors, right? So, and we are quite accustomed with the idea of those complementary colors and the build-up towards the possible representation of all combination of known colors to the human eye in this fashion. And the idea is there that at this stage we introduce color into the whole idea, and why we have a very, very cute oh god, what's the English name for that tiny animal?
Deer?
Nah, that's but the small one, not the big one. Ah, whatever. Right, small deer, right? That's perspective. Sorry?
Deer calf?
Yeah, a calf will do. So let's do. There's a deer calf here, and you actually notice that if you look at the individual points, it semantically makes sense as a deer calf now. But if you look at the individual points, it boils down literally to color information, right? So as you guys know from graphics, and should be intuitively quite accessible. And this is it. So so now all the rest that we do with mobile phones, computers, whatever else, it always boils down, how do we represent what we actually want to show in the simplest form in terms of colors, like lightness but brightness but colors. And then of course we need to think about more abstract concepts, because we don't think in pixels, right? So we want, in fact, the idea of having density independent pixels represents the idea that we want to abstract from the idea of pixels in the first place, but just want to think in terms of shapes, forms, and so on. And what was the first concept to deal with more complex, more meaningful shapes in the context of computer graphics, if you guys recall? What was the first approach to have more construct pictures more systematically, so they can be used in games, for example? Moving images in games, 2D.
Phone is the...
That's the oldest student? No, not that one. Elda, please.
Vertex?
Sorry?
Vertex, perhaps?
No, yeah, that's basically equivalent to the pixel from on a logical perspective, right? So what I'm looking for is like from a conceptual point of view. Okay, older student.
No, that was the name of the small deer. It's foal.
Foal. Okay, cool. Now we know. So foal. F-O-A-L.
F-A-W-N.
Oh, a fawn.
Yeah.
All right. Okay. I need to fix that.
I didn't know that one.
So now we learned everything. So the only thing we learned today is, if anything, blue and black doesn't work. So, okay. Now what I want to get, as you guys all know, that is the idea of sprites, right? So we have, we can capture some sort of semantics like a UFO, or some other objects, trees and so on in a sprite-like fashion, right? So it's a means of abstracting basically from the individual pixels. Is that about correct? Good. So now we know. Cool. So and that has been commonly used in 8-bit games, right? So you have limited color space, right? So we're reduced in the. So when I talk about color space, I'm talking about the ability to differentiate between different colors, right? So based on especially in old 8-bit games. And the sprite is basically a fundamental unit there. So we have some sort of background that is somewhat fixed, and a sprite, so basically a small image that's moving across the background, right? So that was the famous early games such as Time Pilot, Pac-Man. So again, one of those games you may have never played but actually just implemented. And various other ones. Yep.
Yeah, I remember the time when we had, for the very first time, a mouse cursor done as a hardware sprite. Before that, we have to draw the mouse cursor as an image and redraw it on the screen all the time. So when you move your mouse cursor, it would like flicker because you have to, draw the background in place where it was, draw it in a new spot, and then remember what was behind it and like do that. And it was super inefficient and it was super slow and super crap. But then you could do a hardware accelerated sprites, and you could do a mouse cursor as a sprite, which was hardware accelerated, and suddenly it moves on the screen smoothly like we have it these days.
Yeah.
So it was not only, the sprites were not only used for games, they were also used for like trivial things like mouse cursor.
Windowing frameworks and so on. Okay.
Yeah.
Right. Yeah. Good point. Yes, very good point. So sprite, and to animate those, how do you animate those sprites? So if the next step we want to have actually some moving stuff, not only moving across the screen, but actually change shape and some. You want to have running figures and the like. How does the animation work in those old days? You translate to How would you do that? No, very pragmatically. How do you change the shape, let's say, of that UFO at flight time?
Offset the sprite.
Yeah, that's movement but now I want the sprite itself to change. Yes, you're right. So you literally, thank you very much. Yes, so that should have come out of your mouth, I guess. So using sprite sheets, right? So the idea is that you have a lot of little images that capture the entire run of or single animation run of, for example, that plane or whatever else. And the idea is, in addition to moving across the 2D plane, you actually quickly swap between those different sprites by iterating over this sprite sheet, right? So and they give the perception that the actual plane has some sort of is animate in some form. So early days. So that was the. I'm being careful here. 80s, 90s as well, right? So okay. So so 90s as well. And there were some other techniques such as having multiple layers and background that moved against each other. So we have a bit of those parallax effect, like things that are seemingly moving in 3D in front of each other, as known in or seen in Time Pilot. Should I bring that up for the graphics people know that, but I probably should be showing that. So, yep. I will just take a random video I find right now. I'm most likely to switch off the ridiculous music that is usually associated with this. And I just take my. Oh, yeah. So I'm making equitize in my class here. So, but after that, where is it? There you go. That's the one I want to show. So you may sense that, you know, we have a sprite obviously moving around in space and having different animations for different directions, but even the clouds appear as if they are in 3D space, right? Does everyone see that? Right. So, and that's the idea of having multiple layers. You see that some of the clouds are actually connected to a different layer than other than the back layer, the background layer, and so you get the perception as if there's a 3D interaction going on actually, whereas all happening in a 2D plane. So we still know that this from modern web pages, for example. GitHub is using that for 4-page, right? So we have the same principle of having multiple layers, and you get the perception of a 3-dimensional space when you move the mouse. So, but enough of that. Even though I know it's incredibly attractive. So, but let's look at 3-dimensional perspective. So, leaving that behind, how can we move on from there? So, and the fundamental idea, and I pointed it out before, is the idea of a vertex, right? So we have 3-dimensional space, usually 3 axes, x, y, and z, indicating the depth, right? So, and we represent this using, let's say, the usual Euclidean coordinate system using x, y, z coordinates. So, and this should then allow us to link individual vertices and connect them using some sort of material to create surfaces, right? So we have individual points. In this case, we have 4 different points, but they allow us to create 2 triangles or 1 square if you wanted to. But it turns out that triangles are a more flexible mechanism to actually model in 3-dimensional space, because you can represent curvature smoothly. That's the key idea. And many graphics development frameworks, such as here OpenGL as an example, uses precisely that idea, but provides you with the ability to combine individual vertices. Just wait a second, dear student. To individual vertices to create surfaces in different predefined shapes. For example, you can combine vertices in lines or in strip-like fashion, but you can also create more complex things like triangles or triangle strips. And so on. So different forms. Those are primitives basically built into the graphics framework that allows you to specify how different vertices should be combined, right? So do they represent a continuous line, or do we actually represent a surface or a polygon as shown here, which is closed, whereas those lines are open. So would just be a representation of a line. Please.
It took me a while to recall the term. It's parallax effect.
Parallax, that's the one. Yes, parallax effect. So if you have the GitHub for 4-page, okay, now I need to do that. I'm coerced into.
The technical term for that is parallax. So it kind of pretends to have 3D on 2D layered screen. You have it on the phone sometimes as well. So they put icons a little bit above the background. And as you move the phone, you know, it looks as if they are kind of above the background, right? Because the icons move slightly differently than the background.
Is it visible? No, it's not. No. Ah, there you go. Now, when I move the mouse, you see the different layers moving at different speeds, creating this parallax effect. Thank you. Yeah. That's right. Cool. All right. Coming back to real 3D. So. Right, using those principles, so we have individual vertices in 3-dimensional space, and then we have mechanisms or strategies by which they are actually connected, right? So either to form lines, for example, or entire surfaces, as shown here. For example, here's 2 triangles combined into into surfaces that can then be used to create much more complex shapes, referred to as meshes then with the surface, and represent models, right? So I get to that a bit later. So those are one form of the basic primitives, but to go beyond this and say, well, you know, how can you construct 3-dimensional object from vertices and some, different algorithms, if you like, predefined algorithms to combine those. How can we do it in three-dimensional space? And it turns out in three-dimensional space, there's also a set of primitives that you can use to represent nearly any three-dimensional shape. Nearly, of course not, but especially regular shapes often derived by on those four components, or can be modeled using those four components. So a sphere, a cone, and a cylinder, for example. So there's a set more. But anyway, so the idea is then to combine those individual vertices into systematic models, right? By applying a surface, some color, and other stuff like lighting and so on, which we're not talking about. But fundamentally, it boils down, you need to represent triangles, and lots of them, right? So, and combine them meaningfully to get a reasonably smooth surface. You gather already, the more triangles you have, the smoother the surface will appear, right? So, but obviously that will impact performance because you need more vertices to actually perform the representation, right? So leading to complex things such as this one here, which are used for different purposes, but fundamentally have the same challenge. So they are actually modeling complex objects, reasonably complex object in space. This is not quite true for this one here. That's more about lighting. But here, for example, that's the famous Stanford Bunny, right? Your favorite?
It takes a long time to load.
Which one? Cornell box?
Stanford one.
Yes. How many vertices? Yes, you're an expert on this, right?
I have no idea.
Can you just run a count on it? Well, once you
load it first, I don't know.
I register an event listener here. Once you're ready, come back.
I believe it's like 3.5 megabytes, which takes a while to load.
Right. Okay. Okay, that sounds good. So I just know for the scene down here, I think that's 6 million vertices that I use to represent it, and that's often it's used the Runghals model, which is used as a reference model for model loading, right? To see how much performance you can actually deal with in your device. Okay, so I think this was like a super superficial, scratchy perspective on graphics programming in like 15-ish minutes, or perhaps more because of the GitHub 4 pages. But it at least gives some intuition, I guess, how 3D modeling could potentially work, and the way we've come since then. And now I actually want to come back to mobile development and kind of embed it in this context and see, okay, what was the development in the mobile world, and how far is that? Where are we now, basically, right? So this was up to now rather independent of the focus on mobile devices. And as you all know, and have already identified, our favorite game will forever be Snake, right? So 1997. Some people spent many hours playing. I actually didn't, because I found it fairly uninspiring. But
that was the game I wrote first.
Right. You wrote that thing. Okay.
I wrote Snake, yeah.
Well, they all wrote Snake at some stage, right?
So was it your first game?
I mean, yeah. That's, so, but anyway, so that was the idea. So at this stage, programming was done against the specific APIs of the phone model, so was limited level of generalization. Then there was Symbian also, which gave you a kind of uniform platform across, for example, Nokia devices, so you knew what you're coding for Nokia devices and have some manufacturer level compatibility. Was Symbian open source?
Not initially.
They made it, right?
They open sourced it before dying.
Okay.
Yeah.
Right. So you kind of
it was a closed source OS. Yeah.
Right. So it kind of tied down to the platform. And one of the parallel platforms that was reasonably successful was actually Java ME, Java Mobile Edition. So you may recall your fourth semester you had Java. So that Java came in a large variety of variants, right? So the classical Java JDK that we're using, or SE Standard Edition, is basically only the mid-range. There's the Enterprise Edition, which is really rich, providing application programming service, but it's going down to, what's the smallest distribution of Java? Do you recall?
No.
Java Card, was that one?
Yeah, I think so.
I think so. There was the idea you can run Java on smart cards, right? So those.
Yeah,
so,
that's right. Yeah.
So
it was very tiny.
It was very tiny.
Or something.
Exactly, right? So it was very small size. And just in between there was Java ME Mobile Edition, and that was geared towards running on mobile devices, and was actually widely available and somewhat adopted, but not like super successful. But it was the first platform-independent framework to write applications for mobile devices, and with usually more questionable outcomes than meaningful outcomes. Following that, of course, there was slowly a move towards using OpenGL more systematically, and that's the idea was there. Okay, let's use the OpenGL engine, which is firstly platform independent and is available, feature-rich and quite well performing. And how can we bring it to mobile devices? And the idea was there. Okay, we need to have a variant that actually runs on mobile devices, because OpenGL itself is rather heavy with all its functionality, and not necessarily optimized for devices with a small memory footprint, as mobile phones were at that, or yeah, somewhat still are at that nowadays, but even more so were at that particular time. And it became more and more popular to actually use OpenGL embedded systems to program for mobile devices specifically. With the advent of real smartphones, even though Windows Mobile had smartphone capabilities, the uptake was very limited, but it was quite well integrated with the Microsoft ecosystem, so Active Directory and the like. But anyway, it's secondary here. The iPhone was the device that actually brought it to the mainstream market, right? By introducing OpenGL systematically across all its iOS versions. So it became a necessity to consider that one as the kind of default, the go-to development environment for graphics applications, 3D graphics applications on mobile devices. And that has continued throughout the years, so starting with the version 1.1, OpenGL ES 2 and 3 and so on. But as usual in life, Apple has attached some sort of proprietary frameworks for animations, for sprite representations and so on. So here it's important to note that OpenGL is, again, platform independent, right? So it's not tied to Apple at all. It's developed by Kronos, or rather maintained by Kronos, which is a non-profit organization, or let's say more interest group combined usually by graphics cards manufacturers and the like. But it has been adopted in the iPhone first, and subsequently also on mobile devices. But the only downside for iOS, of course, is there's a considerably stronger lock-in, especially if you use the additional frameworks that are available on top of the native OpenGL ES framework. So I'm not sure why there's too much market stuff in here. I skipped that. But what is quite indicated, I felt was quite relevant here, is that there you can observe, looking at the markets that are.
So what's the proprietary name of the Apple's graphics framework?
Ah, yeah. Good one.
It's one of the exam questions. 1 point.
Really?
No, I just made it up.
Let's just put it in and see how many get it right.
Probably not a lot.
Not a lot, no.
Metals.
Oh, I thought that was the graphics, not the animation.
No,
Yeah.
that's just the graphics framework.
Oh,
By the way, metal is compatible with Vulkan, right? So
Yeah.
Peter just talked about this.
Yeah.
So, while the trend for applications on
in fact, it was, I think, a precursor. So Apple started it, I think, and then the Vulkan specs, because Apple is part of the Vulkan as well.
Now it is, but apparently there was a consortium called Mental, right? So, literally. But we just heard about it by Peter. So
Okay.
then they gave up in 2013,
Okay.
and then Kronos took over, because Kronos maintains the OpenGL specification, right?
Right.
So they put it all under one umbrella.
Under umbrella, okay, yeah, makes sense.
But they're all on the boat. I mean, yes, the usual suspects.
Yeah.
So, okay. Apart from the fact, I just wanted to point out, since we're talking about stores here, that the focus on in-app purchases over conventional paid-for apps is considerably rising. So for games, it has become increasingly attractive to have some sort of access to those not only the app platforms but also to frameworks that support this. And you'll be surprised that many of the graphics development frameworks for mobile devices actually may have support for in-app purchases. So it has become a genuine part of the framework itself, as opposed to just doing graphics. So in contrast to the frameworks used on desktop machines, it is much richer and much more integrated, usually in terms of the functionality that's provided. But anyway, just to come back to the graphics train of thought, it's quite a stretch. So so from 1997 Snake to now 2018, one of the recent games like Riptide GP has come really a long way in terms of performance and capability. So and it also has become increasingly easy to actually program for those devices, where Snake was, given the lack of a systematic framework, a bit of a pain to program, but programmable of course. You wouldn't imagine to do that anymore for a 3D world that has the complexity as shown here, right? So so you need to have some sort of helper mechanism to facilitate this. So quite a stretch. So I'd probably give you about how many minutes break? What is reasonable? 10 minutes break is reasonable, apparently. Okay.
7 minutes and 28 seconds.
Again?
7 minutes and 28 seconds.
Okay, 10 minutes. So right. So yeah, let's 10 past here. So then I'll briefly talk about OpenGLAS in greater detail, because of course I was very high level as of now.